Record. Welcome to the Ozeki Journal Club, Perry.
Hey, Carlos.
How's it going?
How about you?
Pretty good, pretty good. Today we're doing a paper. So I'm getting straight to the point this time because we got our first hater on YouTube.
Which I'm excited about, actually.
Yeah, I was pretty pleased. Let's give him a shout out, shall we?
Sure. I don't know his name, though.
If you go on our channel,
Should I do that?
yeah, go on our channel, and I think it was in the Wallets paper.
I think we're doing exactly what he wanted us not to do, though.
Like banter a little bit before. Yeah, you know what? I think he'll be thankful, and then we'll go straight to the paper.
This is a horrible picture of me, by the way. Where's the wallet? This one, right?
Understanding hierarchical deterministic wallets.
So okay, here we go. Jubilee Giggles. Could be a girl. We don't know.
Sounds like a girl. Jubilee Giggles.
So video starts.
For the comment.
Sorry?
Thank you for the comment, Jubilee Giggles.
Yeah, thank you.
We will not talk about hair or Teslas anymore. Quick note, though. Did you know there's a Tesla for $35,000?
Yeah, I think. I know about that. And,
so
and they're saying it's gonna be like the Mercedes, where like I think Mercedes was super luxury before, and then it became affordable, and now no one cares about Mercedes anymore. You know?
Yeah, I don't know if that's a smart move on Musk's part.
Yeah, who knows? He must know what he's doing.
I don't know. Let's talk about it a bit. Okay, yeah. So let's get straight to the point.
Yeah.
No need. Although he was nice and put in the timestamp where we actually started talking.
No, I really appreciate it.
It was useful.
He looked at the video.
Yeah. All right. So today's paper, Perry's going to walk us through because he's the quantum computing expert, and I am really not
expert.
You're an expert. Come on.
I can navigate a bit what's happening here.
Freaking PhD in quantum computing.
That's not true, but we
condensed matter applied
in physics. We'll just say physics, and now we can. I know. I think this is perfect because I know about quantum. I think, and then Carlos knows about computing or maybe neural networks.
Yeah. So I thought it was a cool paper, and also I've been hearing a lot of people sort of saying, "Oh, we're a startup and we're using quantum computing to like outperform people."
I don't know how real that is, but sure, you can.
I think you can comment on that, Perry.
I don't know what they're doing. I don't know if they're doing something like this, but even this is.
From reading this paper, it really sounds like it's very far from being useful.
That's what my impression, but
we'll get into it. But there's also quantum annealing, right? Which is maybe something closer to being useful. I don't know.
Yeah, but I mean, that's the Steve wave machine.
Yeah.
Alessandro knows a lot about this. We should ask him.
Yeah. I thought about him. Anyway, let's introduce the paper. So it's called Training and Meta-Training Binary Neural Networks with Quantum Computing from Abdullah Fawaz at Siemens.
Yes.
Yeah. Paul Klein, Simone Severini, and Peter Mountney. You know this Severini guy?
No, but I just looked at his webpage.
Oh, okay. I thought he was like a quantum guy, right? I mean, I thought maybe you knew him.
No, but he's a computer scientist doing quantum information.
Yeah.
Doing very interesting things. So I think this paper is more about, I guess it's merging two very hot topics, which are quantum computing with machine learning or neural networks. And what's cool about this paper, I guess, is that it goes very slowly into what, I think it's written for computer scientists.
Mm-hmm. It's from, actually, we should say, the KDD conference, which is like a data algorithms conference, 2019. So it's pretty recent.
Yeah, in Anchorage. Okay.
Yeah.
Well,
probably not actually in Anchorage. It's August 2019. Oh no, yeah, it was probably the guy probably got to go to Anchorage. That's cool.
Who knows? But yeah, so I think it's a really like if you don't know anything about quantum, I think you can get a good starting point from this paper.
By the way, Perry, sorry, before you start, you might want to close your messaging there. I don't want to show any personal messages popping up.
Which message?
You have Signal open. Yeah, give it a quit.
Nice.
Oh, sorry about that. All right. Don't want to compromise your privacy.
And I'll quit my actual
message. Ew.
Okay.
All right. I won't interrupt. Go for it. I will have stupid questions though along the way.
No, you shouldn't interrupt because okay, so I guess the point is the beginning starts with a brief introduction of quantum computing or quantum information science and I guess machine learning. And they talk about how quantum machine learning here, aims to find an advantage in applying quantum computing to machine learning. Okay, so that's a pretty vague topic or a vague sentence, but I guess they're going to go into detail about one way in which they think they can leverage quantum computing to help in machine learning. So, okay, yeah, so they talk about these two categories. Okay, so some algorithms promise a revolution in machine learning. Okay, and there's gaps in
theory.
implementation.
Yeah, like if there's a theoretical advantage
to using quantum computers.
In practice, it's still not up to that level.
And okay, yeah, and then there's other things that you can probably do, but maybe it's like, are they useful for machine learning? Okay, so justify their place among well-established machine learning methods in machine learning. So I guess what they're trying to do, I think, is just come up with something that could be implemented and improve on current machine learning algorithms. And specifically, what they're going to focus on are these binary neural networks. And I think maybe you're the expert in this part, but from my understanding, a binary neural network, I'll just go down to the picture. So this is, let's say, a neural network with, let's say, 3 input neurons. And a binary neural network will just be one where the weights are given by either 1 or 0.
I think it was 1 or -1 in this example.
Okay, maybe actually, yeah, you're right. You're probably right.
But yes, I think that's the
okay, yeah, usually plus or minus 1. Sorry,
yeah.
Yeah, so they only have binary values. Okay, and then I guess the main reason they want to look at binary neural networks is because they're mapped. You can map a binary, something binary, very directly onto a bit or a qubit. So a qubit is just a quantum bit. I think that's why they're well, I mean, I think they even state that's why they're focusing on binary neural networks.
I think also they say that that binary neural networks, like even forgetting about quantum, have the advantage that they're very inference is very fast. So like running a forward pass on it is very fast, probably because you can have these like bitwise operations on it. And also I think you can compress the network very easily. Like it's harder to compress a floating point value than a binary value.
Compress? Okay, because I think
I mean, it's in the top of that second page. A great advantage using binary neural networks has a great advantage in compression and inference time.
Yeah. This I really have no idea about, like these binary neural networks and how they help in compression or inference time. Yeah. But I just believe this.
I think that's beside the point. But yeah, I think the main reason for choosing it is because it was just practical to like apply the quantum stuff on it.
And I think at the same time they're showing that maybe they're useful in general. So it's not wasted effort into trying to understand these networks better from the quantum computing.
They do claim like that it's just more annoying, but you could have floating point weights, continuous weights.
But I think, well, I mean, we'll get into that, I guess, maybe. So, okay, cool. So that's the setup. They want to look at binary neural networks, and they want to analyze these systems with a quantum computing algorithm. Okay, and then the point is, okay, yeah, that's just the setup of what they're trying to do. And this quantum computing algorithm is going to rely on something.
Wait, sorry. So to recap, they're trying to use a quantum computer to train a binary neural network, which means they want to find the optimal set of weights to put on the network, right? That minimizes the error. Like,
yeah, I think that's going to be the goal. And then they're also going to, so that's the training part over here in the title. Yeah. And the meta training is just doing this same type of training, but on meta parameters.
Yeah.
So for example, the connectivity of this network.
Yeah.
Over here, like what kind of neural network you should use.
Yep, for sure. Cool.
So yeah, so sorry. So the setup is they want to use quantum computing to train and meta train, I guess, a binary neural network. Okay, and then okay, and that's when so the specific algorithm they want to leverage to do this is something called well, okay, this part is a bit fuzzy for me, but I guess the point is it relies on something called Grover's algorithm. And I think, to the best of my knowledge, I think there are 2 main quantum algorithms, meaning that there are 2 algorithms that result in the speed up due just to the quantum nature of the computing device. So in other words, quantum computing offers a new paradigm for computing, but now you need to come up with a new algorithm that would take advantage of this new paradigm to speed up certain, to give you a speed up over classical algorithms that work on classical computers.
I think this wasn't this supposedly achieved by Google at some point, like last year, where they said they had quantum supremacy?
Yeah, so I think okay, so the point here is that Grover's algorithm has been shown to give a speed up that's order n root n over the best possible classical algorithm
Mm-hmm.
in finding a value in an unsorted list.
Okay.
For example, hashing.
Yeah.
If I give you a hash table and I want to just brute force, well, all I can do to find the input that gives me the right hash is just brute force it, right?
Yeah.
Classically.
Yeah.
If I use a quantum computer, I can get an advantage that goes like root n.
So like, I mean, even a simple problem is like you have a list of integers that's shuffled, and
Yep.
I ask you to give me the index of the number 6.
Sure.
You would normally have to, that would be an order n operation because you'd have to iterate one at a time through each index in the list. With a quantum computer, you would do that in root n time?
Yeah, exactly.
The n is the length of this list? Okay, cool.
Yeah. And the other algorithm, what's it called, is, one sec, you can just Google this, but I hate myself for not remembering the name of this.
Thanks, Jamie.
Shor's algorithm, right?
Sorry.
Yes. Shor's algorithm, which helps you solve these discrete log problems in polynomial time instead of.
That's the one that breaks RSA, I guess.
Yeah, it breaks all these encryption schemes that rely on the discrete log problem.
Do you know if that's like those two algorithms are the maximal set of algorithms that quantum computers can have supremacy over? Like, is there some theoretical result on that, or there's just still haven't been discovered?
So I think people have found there's another algorithm. I can't remember what it's called though. Whatever. I think there are some algorithms that are completely useless though. Like we don't know a good use for them. So we can make up a task where a quantum computer can solve something very quickly, much quicker. But we don't know if that task is useful for anything.
Okay, it doesn't have like a classical analog.
Well, it might, but it's like, is it useful, right?
Okay.
Like maybe, yeah, exactly. So it is the use important? Yeah, the point is you can solve some other tasks maybe more quickly, but those tasks might be irrelevant to anything that's practical.
Mm-hmm.
Yeah, so actually, I think this is Deutsch-Jose that I was thinking of. But yeah, so here are some.
Simon's algorithm.
So here's Grover's algorithm based on, and this is what they get to in the paper, this amplitude amplification.
Mm-hmm.
And this is just a way of saying, okay, well, I guess we'll get into that as we go into the paper.
Yeah, so I guess it starts with like a gentle introduction to quantum computing, right? Which I thought was very nice, for me at least.
Yeah, and they let you they point out an algorithm that you go look up on Wikipedia and get an idea of what it does. But in reality, it's just, I think they even say it. Okay, yeah, so these algorithms can search for an element in an unstructured data set of size n in order root n operations.
So this is kind of like exactly what you want to do with a neural net, right? You want to search for the set of weights in all possible settings of weights that minimizes some function, right?
Yeah.
Kind of.
Yes. I think that's a good way to think about it. And but the thing that's interesting to me is that they're looking at binary neural nets, so binary weights. So in reality, how can I say? If I had continuous weights, I don't think I would brute force every single weight, right?
Well, you couldn't.
That's the point, right? So I think this is a very specific problem maybe that they've constructed.
Like this is a countable.
Yeah, exactly.
Set. Okay.
I mean, okay, we can talk about that later because they talk about how, like you said before, how they can generalize this.
Mm-hmm.
We'd have to read those papers, I guess.
Okay.
But the idea here is to leverage this Grover's algorithm to do exactly what you said: search the full space of all weights to perform this training over for their binary neural network. Sorry. Okay, so then that's the setup now. So we want to train a neural net or meta train it, and we want to use a quantum computer. And the specific neural net we're going to look at is a binary neural network, and we're going to leverage Grover's algorithm to give us our to train this neural network. Okay, now that gets to section 3, which is the part this like, cool little introduction to quantum computing. So they talk about actually how the biggest device, I guess, in the time was 72. Okay, they even mentioned highly imperfect qubits. This is in contrast to a classical computer, which has, you know, megabytes or gigabytes, I should say, of
Bits.
Bits, exactly, classical bits.
What does it mean for a qubit to be imperfect?
It means that if I encode the state 1 in the qubit, or if I think I'm encoding the state 1 in the qubit, I might be encoding a state that's slightly different.
Okay.
Or if I do an operation that, say, an AND operation on 2 qubits that are 1, there's a probability that I don't end up in a 0.
Okay.
Say.
Or a 1, you mean? There's a probability that you end up in 0, not 1.
Yes, exactly.
Yeah. Okay.
For this classical analog.
Yeah. Yeah.
So imagine some of my bits in my classical computer are broken, so that when I add 0 to 1, I don't get out 1, I get 0 by mistake.
Which I guess also happens in classical computers to some extent, right? Just very,
yes,
very
but the issue with these devices, though, in contrast to classical computers, is they have to be kept at extremely low temperatures, which mean near absolute 0. That's one thing. The second thing is you're relying, like any environmental coupling can mess up the whole system very easily.
You mean like the qubit can interact with things that you don't want it to be interacting with?
Exactly, yeah.
Okay.
So like small magnetic fields, if I'm thinking of spin qubits, which are qubits encoded in the spin of a particle, a small magnetic field that just comes from anything can just mess up the whole calculation. Or if I think of, I mean, you're working with, let's say, individual atoms or currents that are extremely small. So very small things can influence and affect you.
Okay, cool.
And that's why these things are imperfect. Right. And I guess, I don't know if they mentioned this here in this section, but they talk about how they're not actually going to do this on a quantum computer. They're going to just simulate the quantum computer using a classical computer. So that limits how many of these fake bits they can use, or fake qubits they can use. And we'll get into why. So let's just get into what a qubit is. So they describe it in, okay, very, very briefly, but the point is, okay, a classical bit can be completely described by 2 states, either 0 or 1. So if I have a classical bit as a current passing through some small wire, there could be current, that would be a state 1, say, and the absence of current would be state 0. Right, so that's very easy to understand classically. I either have something there or not, 1 or 0. In quantum mechanics, though, I can be in the superposition of these 2 states, meaning I can be in a state where there's a probability that the current is off, but also on at the same time. And this is not a statistical property, it's a quantum property, right? So it's not just like there's the probability that my current is on or off. There's a state of the current that's both on and off at the same time, right? So instead of describing my bits as 0s or 1s, as in the classical case, what I need now is 2 complex numbers, alpha and beta. Okay, I guess they're real numbers, but I have to describe my state by a vector that looks like this, where I can fix alpha to be real, and I have a phase phi here that gives me the relative phase between this number alpha and beta. And now what this means is that my qubit is in the state alpha 0 plus beta e to the I phi 1. And if I were to measure this qubit, there would be a probability alpha squared that I'd be in state 0, and a probability beta squared that I'd be in state 1.
Okay, so this part I think was what I was like, it was the newest thing for me.
Sure.
So I guess this phase thing you're talking about,
Right.
okay, I watched a 3 Blue 1 Brown about quantum computing before. So this imaginary value is just like a convenient way apparently to encode the phase and the phase and the periodicity, the I guess phase and frequency of this like state, right? It's like two values that
There's no frequency here though. So the alpha, I would call, like, there's alpha and beta are, I'd say, amplitudes.
Okay, yeah.
And the phi here is the phase.
Yeah.
Which, if I'm just measuring, so what is a measurement? They describe a measurement right here.
Mm-hmm.
So let's say I have a qubit in this state, alpha 0 plus beta to e to the I phi 1.
Mm-hmm.
And I want to measure
before I go on, these, like the bracket thing, right? That's telling you like
this guy?
Yeah. Isn't that some kind of like basis?
Yeah, so you can just think about it like this, as a vector.
Okay.
Where it's like an I hat and j hat, if you want.
Yeah, okay, sure.
In a two-dimensional space.
Mm-hmm.
This is called the Dirac notation. It's convenient for other things, but this is a standard way of describing quantum states.
Yeah.
So, so a measurement, what does a measurement mean? It means verifying if my state is in either state 0 or 1. And if my state was in this state initially, it means that once I measure it, I'll have this right here. The state will be found in the state 0 with probability alpha squared, and the state 1 with probability beta squared.
Okay, so you can almost think of it as like some kind of linear combination, right, of states.
It is exactly a linear combination of states.
Okay.
That's exactly what it is.
Yeah.
But I just want to stress that this is not a statistical mixture.
Yeah.
It's not saying that I just throw some dice, or I just flip some coins, and alpha squared of them end up in tails and beta squared end up in 1. It's I really have one coin, and once I look at the coin, there's a probability alpha squared that it's in heads and a probability beta squared that's in tails.
Sure. Yeah.
Okay. So, once you kind of think about that, this sort of gives you the inkling of what's going to happen with this Grover's algorithm. You can start off with the state 0 being one of your binary weights, the state 1 being the other binary weight, and now you can look at both binary weights at the same time. Somehow, right? You can initialize your system with both weights. So that's the sort of idea behind their proposal. And
so like the amplitudes alpha and beta are things that you can like control in the computer?
Yes. So you can, I guess the idea is the computer allows you to initialize, let's say, a state, alpha, with basically lets you pick alpha, beta, and phi. And then a universal quantum computer, that's the next part, allows you to apply quantum gates to the state, which just means applying unitary matrices to this vector.
Right.
So they give some examples here. We don't. Okay, here they talk about common gates. So the X gate or the NOT gate is just doing this operation. So if I would plug in the state 0 here, I would get what would I get back? I would get the state 1 back, right? Because I would do 0 times 1, 0 times 1 here. That gives me a 0, and then the second row, this with the second row gives me 1. Which is the other state 1, and the same thing would happen for the 1 state. Then there's a Z gate, which just gives me some phase, right? So if I input the state alpha 0 plus beta 1, I get the state back alpha 0 minus beta 1. And this doesn't change the probability, right, of measuring 0 or 1, but this could have some impact. And this is actually, these phases are actually important when you want to do general quantum computations.
But sorry, what does it mean then to have? Does it mean anything to have like this a negative amplitude?
If you just remember that the probabilities are always beta squared.
Okay.
So you take the amplitude squared.
Okay.
The magnitude squared, and that gives you the probability. And these phases, pictorially, we can look at a Bloch sphere, something called a Bloch sphere. Oops. You can describe a state. Actually, we'll get a better picture. Right, trusty Google. Right, so you can think of any state that you can describe in the universe as one of this as a point on a unit sphere. So along Z, say, if I'm this point, I'm exactly in the state 0. If I go along Y, I'm in the state 1 over root 2 0 plus I times 1. But again, if I'm in this state or this state, the probability of measuring 0 is 1/2, and the probability of measuring 1 is 1/2.
So the state space for one qubit is infinite.
I can be any point on the surface of this unit sphere. And why is it a unit sphere? Is because if I add up the probabilities, I have to equal to 1.
Yeah. So, but then it's infinite, right?
There's infinite possible states, yes.
Yeah.
Uncountably infinite possible states I can describe.
With a qubit.
Yes.
So technically you only need one qubit to represent anything. To encode anything.
Again, when you measure though, all you have access to.
Oh, you map to 1 or 0, right?
Exactly.
Yeah.
So if I can measure this qubit infinitely many times,
mm-hmm.
then yes, I can get the angles here
mm-hmm.
to arbitrary precision, say.
Mm-hmm.
Sorry, if I can do infinitely many operations and measurements,
yeah,
then yes, I can do that probably.
Right, because okay, so like if you were to repeat, if you start from the same state.
Yep.
If you start from the same state and you observe the collapse, which is going from to 0 to 1, then you can estimate the original phase, the original like state that gave you that outcome, right?
If all I'm doing is measuring, I can't estimate the phase, I guess, between the two, but I can measure the amplitudes, right?
Right, yeah, but sorry. So then, yes, so you get some kind of statistical thing at the end, right?
Yeah, exactly. So let's say I have this qubit here, or this qubit here plus, right?
Mm-hmm.
I measure it 1,000 times.
Mm-hmm.
On average, 500 will give me 0, and 500 times I'll get 1.
Mm-hmm. Yeah. So then you could encode an infinite number of states, like you said, as long as you do enough sort of repeated measurements
and operations.
And operations.
Because I'd have to distinguish this plus from this minus. Right, and that gives me some phase information.
Mm-hmm.
So I can't just observe the amplitudes. I have to observe somehow the phase, which is something else, which is related to applying these unitaries and then doing the operation and then measuring, say.
Okay.
And again, why are the gates, what we call gates? Gates manipulate qubits, and why they have to be unitary? It's because I want to preserve the probability, right? Probability of a qubit has to be being in any state has to be 1.
Mm-hmm.
And a unitary matrix really preserves the length of my vector.
Okay.
So all quantum operations are unitary.
And they're also invertible.
Unitary matrices are also invertible.
They're their own inverse, I guess.
Transpose, yeah.
Transpose inverse?
Transpose.
Okay.
Sorry. I mean, they say it, right?
Yeah.
1 sec. I should know this, but...
Every quantum gate is reversible in a manner similar to reversible computing.
Yeah.
These matrices
so a unitary matrix is defined by a square matrix whose inverse is its complex conjugate transpose.
Okay.
Yeah. So it's a Hermitian conjugate. Yeah. Okay. Okay. Now here they give you some gates. These are 1 qubit gates. And why are they called 1 qubit gates? Because they act on 1 qubit. Right. Mm-hmm. So we're thinking of 1 qubit right now still.
Mm-hmm.
So this one X flips your qubit from up to down and down to up. The Z unitary just gives you a different phase between the alpha and the beta alpha and beta numbers, complex numbers.
Mm-hmm.
Then you have something called a Hadamard gate, which lets you start off in, let's say, the 1 state, and you end up in this superposition of 0 and 1, an equal superposition.
Mm-hmm.
And the same is true for the 0 state. Okay, these are some simple 1 qubit gates. I mean, they don't get complicated, but these are 1 qubit gates. But you also have something called a 2 qubit gate, or not something called, but you can have multi-qubit gates.
Mm-hmm.
So this C0 gate acts on 2 qubits, right?
Mm-hmm.
2 qubits means my basis is 2 to the 2,
mm-hmm.
right? So I have 4 possible states, right?
Mm-hmm.
So you can, 4 possible states. And if you just apply this to some 2 qubit state, what you'll do is if your first qubit is in state 0, you'll apply the identity to the second qubit, right? That's the upper left square matrix.
Mm-hmm.
So so nothing will happen to the second qubit. And if my state is in 1, the state of my first qubit is in state 1, the second qubit will flip.
Mm-hmm.
So it's a controlled NOT gate,
mm-hmm.
meaning that the first qubit controls the flipping of the second qubit or not.
Yeah, very cool.
Make sense?
Makes sense.
And again, this can be applied to a superposition. I gave you the example right now where the first qubit is in state 0, but the first qubit can be in a state like this: alpha 0 plus beta e to the I phi 1.
Okay, so what happens in that case?
You can just apply this matrix to that state. and you'll see that you'll get some linear
you
you'll
get a
some,
superposition back, basically.
yes.
Okay.
Exactly.
Very cool. What are like in practice, what are the quantum computers using as qubits?
What I worked on in my PhD is something called the spin qubit.
Mm-hmm.
So if you think of a particle, a quantum particle, so a fundamental particle, an electron, say, it has some finite magnetic moment.
Mm-hmm.
And a magnetic moment is just you can think about it as it's something called the spin. Okay, so it's just, you can think about it as an arrow pointing in space,
mm-hmm.
and this arrow aligns with magnetic fields.
Mm-hmm.
So in that case, if we just go back to our picture here, in the things I was studying, you can think of just an arrow pointing here that describes the direction in which an electron is spinning,
mm-hmm.
and rotating this arrow on this unit sphere, or applying gates to this qubit, will be done by applying magnetic fields.
Mm-hmm.
So if I apply a magnetic field along the z direction, my spin will align along the z,
mm-hmm.
and I can initialize the state 0, say, and then I can apply a small magnetic field along y to rotate the spin around y, for example.
Mm-hmm.
And if I apply it for a specific amount of time, I can align it along x, giving me the Hadamard gate.
Mm-hmm.
So this implementation relies on magnetic properties of fundamental particles.
But is there superposition there as well?
Yeah, because if I just apply the small magnetic field, as I just said, along y, for a specific amount of time, I'll
mm-hmm.
rotate along x, and that's a superposition of the states 0 and 1.
Okay.
And I can apply the magnetic field along x to rotate along y, along x to rotate along y, and end up in y, which is a different phase of the same superposition.
Okay.
Just in general, I use magnetic fields to apply my gates, and my qubits are defined by the spin properties or the magnetic properties of an electron, say.
Mm-hmm. And that's like what is being used commonly in sort of real physical quantum computers?
These Google quantum computers that have these 72 qubits, or maybe it's I'm not sure which the 72 qubits are, but they use something called superconducting qubits, which relies on superconductivity.
Okay.
But in reality, all you need is a 2-level quantum system,
mm-hmm.
and a way to transfer your state from these 2 levels.
Okay. Yeah.
So a qubit is synonymous with a 2-level quantum system, if you want,
mm-hmm.
as long as you have control over it.
Got it.
Okay.
So that's it. That's the quantum intro, right?
Yeah, I guess that's it. There's that's the quantum intro. And I guess the point now is what they want to do is just, write a state that has all the possible weights. It's it's a superposition of all possible weights.
Mm-hmm.
And then they just use this amplitude amplification to amplify the state, or amplify the probability of being in the state that will solve my binary neural net.
Yeah. So at this point, this is on 1 qubit, right? Like
this here, no, this is on multiple qubits.
Oh yeah, okay.
Because 1 qubit will give you 2 possible states.
Okay, but in superposition.
Sorry?
2 possible states, but in superposition simultaneously.
Yeah, so it gives me the weight 1 or minus 1
mm-hmm.
for 1 weight.
Okay.
I need 1 qubit per weight,
mm-hmm.
right? So I think they talk about why they use 7 or something, because am I line 1, 2, 3, 4, 5, 6, 7, 8, maybe 8.
Yeah, there's 8 weights.
There's 8 weights. I think they have 8. Yeah. They discuss why they use 8 qubits, and they can simulate that on a quantum. So yeah, again, just to be clear, they're not using a quantum computer here. They're really just simulating these application of these gates. They're simulating that with a classical computer.
Yeah, which they said, I think, for every qubit you need, for n qubits you need 2 to the n,
right? Because every qubit has 2 possible states.
Yeah.
So if I want to describe in general 2 qubits,
mm-hmm.
each qubit can be in state 0 or state 1.
Mm-hmm.
right? So that's 4 possibilities. If I have 3 qubits, each one can be, you can have any combination of ones and zeros for 3 things. That's 2 to the 3. And it scales exponentially, basically.
Okay, makes sense.
And actually, this is also a problem with simulating quantum systems, is if the quantum system, if the system is inherently quantum and you want to simulate it with a classical computer, you need exponential amount of memory and storage, right? But if you had a quantum computer, you would need exactly the number of bits as there are bits in the thing you're simulating. So if every qubit representing the weight is set to a superposition of all possible values, then the entire cost landscape is contained within a quantum state, which has been generated using only a single quantum circuit. So they're using a quantum circuit, which they have an example of here, which is just like I don't know if in classical computing you use the term circuit, but what this just means is, for example, you start with on the left, it like the x-axis is time, and the y-axis is just the number of qubits or different qubits. So if you look at the inputs here, there's 0, 0, 0. As time evolves, you apply some unitary called U input. You have allowed to all 3 of these qubits. You wait some extra time, then you apply some additional unitary that acts on these 6 things. Wait some additional time, and then apply some other unitary that acts on these 4 things, and then do some controlled operation to output something at the end. So these circuits are just read like that. The x-axis is time, and you have description of the qubits along the y-axis.
So this is an example of what's going on for one neuron of the neural network. It accepts 3 inputs and then applies the weights to it, and then an activation.
Yes, but I think sure. I think this is
on the left, no?
Sorry. Yeah. So yes, but I think this is for specific maybe classical equivalence. Yeah, so this is for the activation function. They're trying to implement something specific, which I guess actually that's the only thing the neuron does, though. So yeah, so you're right. It's just the application of this procedure here.
Okay.
And they go into some level of detail of how they do every part of the operation, which we can go through, I guess. But I guess the main idea is you construct a linear superposition of all possible states. And then you apply this Grover's algorithm or this amplitude amplification. And all that's going to do is going to take you construct a state that has alpha 1, beta 1, alpha 2, beta 2, alpha 3, beta 3, right? Then you construct some mega vector, right? That goes like 2 to the 8. 2 to the 8.
Like
entries. Classically, yeah.
Yeah.
And then classically, you can mimic the application of this Grover's algorithm. And what you're going to do is just amplify the probability of being in a state that solves or that trains your neural net. And then when you measure that state, when you measure your state, you're very likely to be in the state that trains your neural net, basically. Yeah. That's the idea behind this whole procedure. Okay, and then So
what you're searching for is like on the quantum level, you're searching for some setting of alphas and betas, right?
No. Like so
you need to set those correctly so that then you have a high probability of outputting the correct final state.
No. So what you're going to do is you're going to apply Grover's algorithm. Yeah. To make it so that you end up in a state that's very close to being exactly the state that trains the network.
Yeah, but that means then setting getting the correct quantum state, so that when you decode or when you read, when you make the measurement, so you're amplifying the amplitudes such that happens, right?
Yeah. So if you look, they have the pictures here, right?
Yeah.
So imagine these are the alphas, the betas, gamma, delta, epsilon for being in any possible superposition of.
So you start uniform, I guess, right?
Yeah. So exactly. So let's say let's say if we just think of 1, 2, 3, 4, 5, 6, 7. So these are 3 qubits, say, right? So let's say this is 0, 0, 0, 0, 0, 1, 0, 0, 0, 1, 1, all the way to 1, 1, 1, right? And let's say the real thing that maximizes or that trains my neural net, is the configuration that's like 0, 1, 0.
Mm-hmm.
And that's described by this amplitude here. By
Mm-hmm.
applying this Grover's algorithm, or this amplitude amplification, I should stop calling Grover's algorithm.
Mm-hmm.
What happens is the weights get readjusted. So
Yeah.
now, so if I were to measure the state of my system here, I would be equally likely to measure any of these possible configurations.
And now it's a statistical likelihood.
No, it's never.
Oh, sorry, no, you're right. It's a quantum.
Yeah, it's quantum
property. Yeah.
Then I apply my Grover's algorithm. The amplitudes have readjusted.
Yeah.
And if I measure it here now, I can still measure any other weight, but chances are I'm more likely to measure this specific good weight.
Mm-hmm.
And if I just keep doing it, eventually all the weights can drop to 0 or close to 0.
Mm-hmm.
And I'm very likely, 99.9% maybe, to observe the correct amplitude, to observe the correct state.
Mm-hmm.
And the idea here is, I guess you can do it 2 or 3 times. And if you're in this kind of likelihood, then eventually you'll be sure that you're in the proper configuration with some high probability.
Mm-hmm.
Okay, and that's the idea of this whole thing. There are some steps that are non-trivial, I guess, that describe over here. So, for example, representing, they talk about how, I guess, these floating point numbers also. So other parts of our construction are, however, incompatible with non-binary inputs. Okay, so they talk about representing numerical values with.
I think that's just like converting everything to quantum, right? Like applying the weights to an input, representing values, and using an activation function. They just use the correct gates, the correct quantum gates to achieve that, right?
Yeah. So here they just talk about, though, if you want to do floating point weights, I guess.
Mm-hmm.
There's some standard way, which is in reference 20. But they also talk about how this, the other parts of the construction is restricted to binary data.
Mm-hmm.
Well, I mean, I think the main point of this is just to understand that the idea is exists a quantum algorithm that lets you search this thing better than just brute forcing it.
Mm-hmm.
And that's given by this amplitude amplification.
Mm-hmm.
And actually they talk about in equation 3, they tell you how this thing scales. So you can over apply this amplitude amplification.
Mm-hmm.
But the point is, you know how it goes. It goes like sine squared of 2k plus 1 theta, where theta is given by the initial probability.
Do you have any like intuition on the previous equation, like the Q operator thing?
This one?
Yeah.
Okay, yeah, this I had to look at actually, but
like that's the one, that's the amplitude amplification, right?
Yeah. So let's see. Okay, so basically this is a huge matrix.
Yeah.
Right. So you apply this operation, then this one, then this one, then this one, right? On your vector, that would be on the right.
Mm-hmm.
Okay, actually, I mean, they even say it. Q is a matrix. Oh, it's the matrix.
That's the neural net, right?
Yeah. So you'd input your state, and this is the yes. Yeah. So okay, they say the operations S0 and S chi. The form of S0 depends on our initial configuration. Yeah. Okay. Actually, to be honest, I didn't look at this in detail.
Does S chi defines what states the search will look for? It corresponds to those with an accuracy of 100%, which is a controlled Z gate. So there was like this, I think we didn't go over it, but there was like the formulation for like checking whether or not the neural net's giving the correct output, right?
Okay, maybe
it's
okay. There's calculating accuracy, you mean?
Yeah, that part.
Sure. I mean, we skipped this whole problem statement, right? So they actually want to look at some specific problems, which are given here. Okay, yeah. So let's just pause. So the idea is they want to use amplitude amplification to do this basically, to amplify the amplitude of being in the proper state.
Mm-hmm.
But what does the proper state mean? Well, they have some way of getting the proper state, or the state that they want, and that's given by these things here. And they discuss the intermediate steps in these bullet points.
Mm-hmm.
So implementing the activation function. So it's like a CC NOT gate. Again, okay, to be honest, I didn't go through these in detail. I just believe that they can do this.
Yeah.
But
I think the important part was like the accuracy thing.
Okay, we can look at that.
Yeah.
For each data point on the training set, we must compare the prediction to the label in order to find the accuracy. We achieve this by running the QBNN with the weights in superposition for each point in the train. Okay, we said that already.
Yeah.
Each time the output of this QBNN is stored in a different qubit. For a training data set of size n, we obtain a register of n qubits containing the predictions of the QBNN for each of those n data points.
Mm-hmm.
Since the labels are binary, we can represent the accuracy of each of these by performing a NOT gate on all of these qubits corresponding to a data point with a label of 0. We can represent the accuracy of each of these by performing a NOT gate on all of these qubits. Okay, this sentence is
yeah, I didn't get that. I had to read that a few times, and I still don't really get it. It says it's easy to see that this gives a simple method for identifying correct and incorrect predictions. Each qubit in the register will be in the state 1 if it corresponds to a correctly classified data point, and 0 if it does not.
Okay, wait up. So maybe they have maybe that's what this is here.
The ancilla.
Yeah. So
they didn't really describe what it actually does. The ancilla. They said it's just like some helper thing, and that's it.
So ancilla qubits are usually qubits that you just use to perform some task, but you don't measure them at the end.
Oh, I see.
They just do some like here they just entangle with these other qubits, and then you use them as a knot to do something.
Oh, okay.
But what you really care about is the output qubit.
Right. Okay, but I mean, I think whatever. We can just assume that they end up like they run their neural net. They end up with like one qubit for each input, right?
That's what they start with, right?
Yeah.
1 qubit for each input. That's the state here.
Yeah.
And the point is they can apply this matrix, which I'm sure we can calculate what it does exactly by going through the steps here, these anti-CNOT gates and all these gates.
Mm-hmm.
It's just a product of a bunch of gates that will lead to an amplitude amplification given in these figures.
Mm-hmm.
Yeah, so you see operation Q must be applied repeatedly to find the target state.
Mm-hmm.
But the action of target Q is sinusoidal. So you're applying this repeatedly, but it's sinusoidal, and this is the relationship. So after K amplifications, it goes like sine squared of 2K plus 1 theta, where P and theta obey this relationship, and P is the
probability of...
Yeah, the initial probability of obtaining the correct weights.
Yeah.
And okay, and they see this. They say that behavior.
Like they say that this somehow scales exponentially with the size of the problem.
For classical computers, sure.
Oh, is it? Because it says, in other words, a harder problem with more weights to search requires a greater number of quantum amplifications to find.
Oh, sure. That's just because I think P gets smaller, right?
Oh, I see. Okay. Right.
And then as for small p, sine squared goes like p squared or something.
Okay.
So if p is small, you need to. It's very small angles.
Oh, okay. Yeah, that's interesting. I didn't get that. Cool.
Yeah, and then it's just like results, right?
Yeah, I think their main result was like, yep, it actually is sinusoidal, and they did manage to get 100% accuracy.
Again, yes. I mean, it's just sure. The thing that's interesting to me, I think it's interesting in the sense of machine learning also is that this meta training, right?
Mm-hmm.
Where they actually see these. I couldn't actually map these networks to the problems that they were discussing up here. So we should say one problem is the output should be the sine of x3 times x1 plus x2, and the one should be the sine of x1 plus x2 plus x3.
Yeah.
And somehow they say that these networks. I'm skipping a bunch of things now because they also talk about meta training, right?
Very briefly.
Yes, I think they just point out this basic idea that you can also do superposition for the connectivity of the networks.
Mm-hmm.
and then just do this optimization or this amplitude amplification again, but for these connectivities.
Mm-hmm.
And that should give you a similar thing. You're just leveraging, again, this Grover's algorithm, just searching, instead of brute force searching, you can search in some faster, in some root end time instead.
It's pretty interesting because like usually in like classical machine learning, you're very constrained by having some sort of like differentiable objective, you know? So like
So they talk
searching,
about that actually
yeah, they do.
in the conclusion.
Yeah, and then for example, like for picking, you know, what connectivity to have on your neural net, you usually lose differentiability there, and you're basically in brute forcing, right? But here it seems to like not matter at all, right? Which is pretty cool.
I mean, it does matter, right?
No, because it's really like a better enumeration.
It's root end.
You don't need like any like landscape properties to hold.
Right, but you get a root end improvement over just brute forcing it, I guess.
Yeah, yeah. Which I guess is not a. It's not a huge improvement, right?
No, but I guess if you look, the example they give is usually Bitcoin, right?
Yeah.
If you had Grover's algorithm, you can hash much quicker. You know, instead of 10 minutes, you get root 10 minutes or whatever, and you become rich, right? It's done.
Sure, but I mean, I guess.
My point, my point is that the root end could be important. The scaling is not good, but it could be important for real life problems.
Yeah. Mm-hmm. I guess it'd be interesting if they had compared it to something like gradient descent, which they don't do.
But they can't. Everything is binary here, right?
Yeah, I know that's true. But it would have been cool. I mean, I think it'll be interesting to see like the next evolution of applying this to a continuous system.
But they talk about this.
Yeah.
Derivative. Sorry.
Well, I mean, the annoying thing about the gradient descent is that it's like a local search like algorithm, right? So it's very vulnerable to local minima.
Yeah.
So I think like it's introducing an extra variable, which is like speed of search versus like optimality of the search, right?
I don't get that. What do you mean?
Like, I think you can run gradient descent for an infinite amount of time and still not get the optimal solution.
That's true.
That's not the case for something like this, right?
But I think the equivalent to this though would be just brute forcing the whole thing, right?
Yeah, for sure.
And the question then is, how much time do you save? And it's root n.
Mm-hmm.
And I think the important thing here is they're just showing you. Okay, the important thing is the thing we're skipping basically. They're showing you the steps, like how to construct this neural network properly.
Yeah.
In this specific example, like Grover's algorithm is known for a long time, right? And this amplitude amplification is also known.
Mm-hmm.
They're just taking that concept and applying it specifically to the neural network.
Mm-hmm.
It's just seeing the parallels and putting the problems on top of each other and identifying the differences.
Yeah, for sure.
Again, I'm sorry that we couldn't. I didn't spend the time. I should have maybe spent more time looking at this, but yeah, the idea here, I guess, is that you can, they talk about the probability of success. I mean, they just achieve better. Yeah, go ahead.
No, for sure. I think like you said, what they're doing is really applying very well-known concepts to like a new domain. But I think what I wanted to get the most is like an intuition on like why the quantum framework provides this root n speed up, right? So like why this amplitude amplification thing works. Like maybe if we forget about like the specific instance of problem, which is like neural nets.
But that you can just look up Grover's algorithm.
Yeah, I guess. But I mean, there must be some like intuitive thing, which is like, okay, well, you have this like idea of superposition, right?
Yeah, that's what it is, right?
Naively, I think about it as parallelization somehow.
Yes,
right?
You can think about it like that. I think that's commonly what people think about.
Yeah.
But it's parallelization with a probability on top.
Mm-hmm.
Right? It's not just like I run everything on everything.
Mm-hmm.
I end up with a probability distribution, if you want, over measuring the proper thing or not.
Mm-hmm.
You know,
Yeah,
even
for sure.
here, right, the probability of getting the right thing is very low for low number of iterations.
Mm-hmm.
But probabilistically, it goes up as you keep amplifying.
Right. Yeah.
But even up
So
here, there's a probability of not getting the right answer, say.
for sure. Yeah. I mean, I guess like I still don't have a good intuition on like how do you go about like amplifying about the amplification process, like what
Like,
tells you what to amplify and what not to amplify, basically.
yeah, that's the construction here, right?
Yeah.
It's really based on the problem you want to solve. So it's based on this problem.
Mm-hmm.
Yeah. So again, this, if I'm not mistaken, is what's it called? Supervised, right?
Mm-hmm.
So
Yeah.
you know the answers, and then you can just check by applying this network.
Mm-hmm.
It's again we have to be very careful in calculating the accuracy stuff.
Yeah.
But they really discuss how to construct these matrices. And I think if you can apply these matrices, if you just apply this to that vector,
Mm-hmm.
you'll see the amplitudes increase
Mm-hmm.
for the optimal solution as you apply.
Yeah. Yeah.
And I guess the intuition is given in these little small paragraphs here, or the attempted intuition.
Mm-hmm.
But again, I think we have to read Grover's algorithm carefully to understand everything.
Okay.
To get some intuition, I guess.
Yeah. No, I'm like
I'm
asking you like this is something you do every day, but probably not.
Oh no! Like again, I was more. What I did was looked at more of these like practical like implementations of qubits and stuff.
Yeah, for sure.
Not how to use them, because I think we're kind of far from, like, people factor the number 8 and they're like, oh my god, we just factored the number 8 with a quantum computer. You know, like it's like we're very far, I think, still from getting. I mean, there's a quantum computer that you can submit jobs to,
mm-hmm.
that Microsoft has.
Mm-hmm.
But it has like I don't know, 16 qubits maybe or something. Open quantum computer, Microsoft. Yeah, I'm not sure actually.
Maybe like cloud quantum computer.
Is it cloud?
Oh, there it is. Experience quantum impact today. A scalable open approach to quantum solutions and development. Azure Quantum.
Oh, yeah, okay, there's one qubit stuff,
yeah.
But they have, I don't know, cloud quantum computing. Quantum computing. Yeah, IBM quantum. Okay, it's not Microsoft. IBM. There's this guy right here.
Mm-hmm.
And if you look at this picture, maybe I can look at the component. Yeah. So you see what you do. Here's your qubit, right?
Mm-hmm.
And then you can apply gates.
Yeah.
You know, and then to this qubit, and then you can take this one and put it here, and then say like, I have a control, like this kind of gate. You know, and these are just gates that you can apply.
Mm-hmm.
Put some phases on everything. And at the end, you get a probability distribution, right? Like here, like measurement probability.
Mm-hmm.
Okay, it hasn't, I guess, updated. I don't even know what I did here. But the point is, at the end, you get some distribution of all possible states.
Mm-hmm.
And it just turns out that people have figured out that by applying matrices in specific ways, you can control the amplitude of the output state,
mm-hmm.
to have certain properties.
Right.
So yeah, it's just linear algebra, right? You figure out what kind of matrix I'll have to apply to get some desired property for the output state,
mm-hmm.
or hide a big number for the amplitude for the desired output state.
Yeah.
And then I just apply that matrix multiplication.
Mm-hmm.
And at the end, probabilistically, if I just associate those amplitudes to probabilities, I'm likely to get the thing I want.
Right. I see.
But
okay.
I don't know the details about.
Yeah, no, I think that's what I missed. I think I missed like how the operator matrices relate to the amplitudes of the state. Right? Like, how does the amplitude get affected by applying a NOT gate?
Oh, but that you can just do, right? You can just look at this. This is what a CNOT gate does, right?
It's just a matrix multiplication at the end.
Yes.
With like non-zero one entries on the vector that you're applying it to, right?
Exactly.
Yeah. I see. Okay, cool. No, that makes sense.
I mean, the point is applying this, right? Let's say you have alpha, beta, gamma, delta.
Yeah.
Could mix a general unitary matrix could mix alpha, beta, gamma, and delta, right?
Mm-hmm.
To give you something that's higher than all of them, say.
Mm-hmm. Interesting. Okay, cool. Yeah, I mean, I think this is making quite a bit more sense now.
And I should say that you can. There's a theorem that says you can describe any unitary, say, on two matrices. If you have three 1 qubit gates and one 2 qubit gate, specific 1 qubit and 2 qubit gates.
Mm-hmm.
But I think these four matrices are enough to describe any unitary operation, or the combination of these four are enough to describe any unitary operation on the 2 qubits.
Mm-hmm. I see. Cool.
Yeah. So sorry, I didn't. I should have maybe went into greater detail about the actual this stuff here. But I guess from my understanding, the idea behind this is you leverage the property of quantum computers to be able to do this linear superposition,
mm-hmm.
and to be able to search within all parameters of this list of possible weights, to be able to at the end amplify the amplitude of being in the specific configuration that trains your neural net, and then you just measure the configuration, mm-hmm. and you're very likely to be in the configuration that actually trains the neural network.
Yeah. But I guess I don't know, I always think in terms of like the classical like gradient approach, right?
Okay.
You would like measure the performance of your weights.
Yep.
And then you measure like how far off it is from what you want, mm-hmm. and then you update according to that, right? Like there's kind of like a two-step process, which I'm guessing also kind of is happening here. Like, are you measuring after each application of Q, are you measuring the output state?
Okay, that's a good question. Okay, yeah, so I think the point is, yes, every time you apply Q,
mm-hmm.
I mean, you just change, like one application of Q gets you from figure A to figure B.
Mm-hmm.
Is that your question?
Yeah.
And then the second application, say, gets you from figure B to figure C.
Mm-hmm. For sure.
And then there's an optimal number of applications for which you'll maximize this configuration.
So it depends, like this process always depends on what your neural net outputs, right?
Your neural net outputs this basically.
Mm-hmm. Yeah.
For the weights, right? These are the weight configuration.
Mm-hmm. Yeah.
Oh wait, maybe I'm misunderstanding your question now. At the end here, where are we going? At the end here, you get a number, right?
Mm-hmm.
The weights give you what happens at these black dots.
For sure.
At the end here, you get a number.
For sure.
And you're saying you want to compare that to something.
Yeah. You apply your neural net, you get a number.
And then you update the weights.
Number is good or bad. Depending on whether it was good or bad, you update your weights, right? If it was good, you don't need to update your weights.
Sure.
Right.
Yes. That I think that's what they do here in this accuracy. I lost it now. They're calculating the accuracy thing.
Mm-hmm.
See, each time the output of the QBN is stored in a different qubit. There's like training here, right?
Yeah.
Except I don't understand. Okay, again, this sentence is a bit weird for me again.
I know, and I felt so stupid reading it because it says right after, it's easy to see that this gives a simple method, and I just didn't get it.
Yeah.
Okay, but I think you pointed out something I missed, which was like, at each time you store the output of the bit, like you get some sort of like time series of what a single input is doing.
I don't know if it's a time series, but I guess it's a different, for a different input, you get a different.
Yeah, well, no, it says we achieve this by running the QBNN with the weights in superposition for each point in the training set separately.
Yeah.
Each time the output of the QBNN is stored in a different qubit.
Yeah.
So you get like a vector of outputs for the same input, right?
I thought it was for each different input. You get
That's what I thought initially, but now that I read this, it sounds like you look at each one separately, each training point separately.
Yeah.
And then you get like wait, no, that kind of makes sense. You should always give the same one, right? Oh wait, no, maybe not, because of the superposition thing.
No, so it says each qubit in the register will be in the state 1 if it corresponds to the correctly classified data point, and 0 if it does not.
Yeah.
So your vector has just all the corrects, like yes or no, ones or zeros.
Mm-hmm. Right. And okay, for n qubits, you get, for n data points, you have n qubits at the end. Okay, fine. Yeah, then I messed up.
But you're right. Actually, I'm a bit confused now. Where you're right. Where does the update happen, right?
Yes.
Did I just gloss over this? Maybe I glossed over it. Like I'm not. Yeah. Okay. I don't see it connected to this equation here right now.
Yeah, I think that Q equation is the key.
I mean, it's for sure the key, but
but I think we can understand it like in terms of Grover's algorithm applied to something trivial, right? Like if you're just searching for a number in a list.
Yeah.
The same intuition should apply, right?
Okay.
I'm assuming. So
Maybe.
I mean, I think you're right. It just comes down to understanding Grover's algorithm.
Yeah, for sure. But I just want to know. I don't know where they mention like there is a mention of this training over here, right? Of this like getting the output and checking the accuracy.
The only one I know is in like that paragraph on calculating the accuracy. And then after that is this thing on taking, like applying this Q operator to this like state vector.
Mm-hmm. Let's make sure I didn't mess up here. Like, yeah, this is the W is the state of all binary weights. That's your initial state, right?
Mm-hmm.
Okay, sorry. And then OW is the outcome of the neural network given by the set of weights.
Mm-hmm.
Right. So there's two states here.
Yeah. W and OW.
Yeah.
Sure.
Sorry, this is the part, I guess.
Oh yeah. One sec. The output of a circuit would then be the quantum superposition of all possible values and their respective outcomes.
Exactly. Yeah. That's
I see. Yeah. So, okay.
So everything is encoded in the state.
Yeah.
And then you just apply these matrices, right?
Mm-hmm.
To this full state. And by the way, just to be clear, when you have two kets like this,
mm-hmm.
It just means like add another qubit that has this state in it.
Like you concatenate them?
Yeah, exactly.
Okay. Right.
So you have another qubit that just tells you the output.
Mm-hmm.
So okay, yeah, that's the. I should have said that. I should have just read this like.
But why are they summed here?
You're summing over all possible configuration of weights.
Yeah.
So if you had one weight, right, you'd sum over the configuration would be 1 or 0, right?
Mm-hmm.
So you'd sum over 1 or 0 and 0.
Yeah.
And the weight would be alpha, beta, right? Or 1 over root 2, 1 over root 2.
Mm-hmm.
So your initial state is a linear combination of all possible configurations of weights and the corresponding outputs.
Yeah.
Right. So if I have 3 qubits, that's why. Okay, I mean, I even went through this, but if you have 3 qubits, you need a fourth that gives you the output, right?
Mm-hmm.
So your initial state will have 4 qubits in it.
Okay. Yeah. Right. And that's what you're searching over.
Yeah, you're searching over the full space of weight configuration plus output of the given those weights.
Mm-hmm. Yeah. Okay.
So you're even running the algorithm as you. I mean, yes, this is your initial state, and then you go ahead from there.
Mm-hmm. Okay, so then the last thing is like how that connects to this Q operator, right?
How they construct the Q operator from that. I think we have the ingredients now, though, right?
Yeah.
We have both the weights and the outputs given those weights.
Mm-hmm.
And then I think I can just imagine that I wanna amplify the thing that will give me the proper outcome.
Yeah.
I have some property for the final outcome that I
Mm-hmm.
want to amplify, right?
Mm-hmm.
So given that I have a property, I can construct a matrix that amplifies the amplitude for having that outcome, or having a qubit in that state,
Mm-hmm.
or a set of qubits in that state, a set of qubits in those states,
Mm-hmm.
and then what comes out with it will be this W ket over here, this W vector
Okay.
here.
Okay. Yeah.
That was the missing ingredient, yeah.
Yeah, there we go.
So I have some property that I want to maximize, or that I want to amplify.
Mm-hmm. So that's this like S chi.
Yeah, in terms of these S chis, I'm not sure, but yeah, maybe. The formula 0 depends on the initial state configuration, but the formula chi defines what state the search will look for. Yeah, okay, yeah, there you
go. Mm-hmm. Which like that's your like target data, right? That's your target outputs. Yeah.
Exactly.
Like you can write those down.
And then you say, in this case, our target state corresponds to those with 100% accuracy.
Mm-hmm.
Okay, then I tell you what S chi should be.
Okay, cool. Makes sense.
Controlled Z gate performed on each of the target qubits. I think we have to look at this more in detail, but I think that's the idea, though.
Yeah.
You play with the phases of those things and then amplify, maybe.
Mm-hmm.
Yeah, okay, it's all written out. I mean, obviously it's written out, but I should have been more careful with that.
No, I think I'm getting a better feeling for it now. This is cool. And like this would like a procedure like simulated annealing be something else that you can use on this kind of thing?
I think simulated annealing.
Yeah. Isn't that where you just like have some set of electrons and like they on their own physically go to a ground state, and that ground state encodes some solution, right?
You mean quantum annealing?
Sorry, quantum annealing. Yeah, sorry. Simulated annealing I think is like the classical analog.
Yeah, so
quantum annealing. Yeah.
The benefit you have with quantum annealing is that you can tunnel out of lines. Like the problem with annealing in general, or simulated or gradient descent, if you want,
mm-hmm.
is that you can end up in the local minimum,
mm-hmm.
and then once you're in the local minimum, you can't get out.
Yeah.
One property of quantum mechanics, though, is that even when you're in a local minimum, like your particle is in a box.
Mm-hmm.
There's a probability that it tunnels out.
Mm-hmm.
So even if I ended up in a local minimum, which is like a box,
mm-hmm.
there's a probability that I leave that box.
Yeah.
In search of another better minimum.
Well, do you leave that box to some other random point?
Well, if I just measure the probability, if I measure where the particle will be at a later time,
mm-hmm.
there's a probability that it won't be in the box.
Yeah.
There's a distribution of possible mm-hmm. new positions it'll be in. And that distribution will include, hopefully, another minimum.
Yeah, for sure.
That hopefully is smaller or more global or a better minimum than the one I would have been confined in if I didn't have a quantum system.
I mean, usually this is already something they do, right? Like when you do gradient descent, you can sort of like in parallel start from many different random points, or like randomly go to another point, right? Sort of classically.
Sure.
This is a way to like get a better coverage. Right?
I guess the advantage of, I mean, in the quantum annealing case, it's a quantum property, right?
Yeah.
I'm not just initializing a bunch of different particles. I'm just starting with one particle,
mm-hmm.
and there's probability it can leave the local minimum.
For sure. Yeah, exactly.
And thermal annealing is slightly different. I don't rely on the quantum property to leave the minimum. I rely on thermal fluctuations to give me enough energy, say, to jump out of the minimum.
Cool. So you could imagine something similar happening with training a neural net, right? I mean, maybe there's papers that are on.
Yeah, but maybe. But I just want to stress that I think it's different that in this case, right? Because they're countable configurations. Right?
Oh yeah, for sure.
Okay. So this quantum annealing, there are for sure papers that look like D-Wave and quantum and,
Mhm.
and training neural nets or something, you know?
Yeah, yeah. Okay. Very nice. Very, very nice. Well, I think that's it, eh?
Yeah, I guess that's it. There's some conclusions that they discuss, like how this is different, like gradient descent is a bit different. I can't remember exactly where it is. I should have highlighted everything, but yeah, okay. They talk about overfitting here and how they choose 100% accuracy, but in realistic cases, it might not be good to get 100% accuracy.
Yeah.
Okay, the input is binary. Okay.
No, that's it. And also, like, their
Oh yeah,
neural
sorry.
net is tiny.
Sorry.
Their neural net was tiny.
Sure, but this is the thing I was talking about.
Okay, yeah.
So they in reality they can do this backpropagation, right?
Mm-hmm.
Because in reality your list is not unstructured.
Exactly.
Or your landscape is not unstructured. You know that if you go in the direction that minimizes or that reduces your cost, you're going towards the minimum.
Mm-hmm.
So you have some structure in your list.
Yeah.
So I think here, which is important, they're pointing out the distinction that in here we're really considering cases where the list is unstructured or the landscape is unstructured.
Mm-hmm.
And in that case, you expect the quantum speed up. But we're not sure if we expect one in the structured case where backpropagation or just like gradient descent is applicable.
Yeah, that's why I think I brought up quantum annealing, right? Because
Okay.
I guess in quantum annealing, you do have the landscape as part of the problem.
Yeah, but okay, again, but there's an encoding. I don't know anything about this, so I'm not gonna.
No, that's fine. No, but that's a good point, right? Like, I think maybe it's not a fair comparison to look at this versus gradient descent, right? Because this is fundamentally using less information. Again, forgetting that these are binary values.
But I think the point is all they've established, I think, or what could be established is that if you have unstructured, like if you're in binary trees or binary neural nets,
yeah,
you get this root n advantage.
But could you say that a binary neural net, like the weight landscape or the error landscape of a binary neural net, is unstructured?
I think so, isn't it?
I mean, maybe I would imagine that, like, the set of weights, if you looked at it as like a big vector, that gives you the best solution, is like, in terms of distance on that vector, pretty close to a solution that's like epsilon away from the optimum, no?
What's epsilon here? Epsilon, they're integers.
Like, right? Maybe if you flip one bit, maybe your neural net's not as terrible as if you flipped like 50 bits. I don't know.
But I can really imagine that it's very bad also, right?
I guess, yeah. Yeah, I mean, you can flip like the last bit at the end that completely undoes everything.
Yeah, exactly.
Yeah, that's true. Okay, so yeah, you're right. Maybe it is unstructured.
I guess in general it's unstructured.
Yeah.
Maybe you can construct examples where it is structured.
Mm-hmm.
I guess the point is where you would have to apply brute force, you would get the advantage with quantum computer.
Yeah, definitely. Because, like, I guess this root n advantage might be a lot less than the advantage of considering the structure of the landscape, right?
Yeah, they talk about that here, and they even say like maybe like we can get a quantum. We conjecture that a quantum search method that applies quantum advantage to structured searches, if it exists, can be applied to the cost landscape in place of the quantum amplitude amplification.
Yeah.
So they're saying maybe they can come up with a quantum algorithm that takes advantage of the structure as well.
Sounds like a big challenge.
One thing is I am always confused because it seems like we're getting very ahead of ourselves, you know?
Oh yeah. Quantum computers are like, wait up, like we're not
close to doing anything useful yet, you know?
Yeah. But I mean, theory can go as fast as it wants to, right?
No, I know, but yeah. I guess I can imagine a situation where maybe we don't get a quantum computer that's useful at all, you know?
Sure.
And then we did all this theory for nothing. Not for nothing, but
no, I see what you mean.
Like now we're applying it to very simple, like, I don't know.
Like assuming that there will be a quantum computer that's powerful enough, this will be useful, but it might never exist, right?
Yeah, exactly. So assuming there will be a quantum computer powerful enough and that binary neural nets will be good.
Yeah.
For some problem.
Well, what I found surprising was that, like, it's very hard to simulate a quantum computer, so they use an 8-neuron neural net. But it was also very difficult.
Is it 8 or
like,
6? 6,
I think
right?
it's
or 3. 5, no? 1, 2, 3, 4, 5.
Oh, sorry. What was there? 8?
Oh, the weights. Okay,
Oh, 8 weights. Okay, sorry. The number of connections. Sorry, 8 connections. So they used 6 neurons, not just because it's expensive to simulate that number of neurons, which is what was it 6, right?
It's 5, I guess. Oh, I guess the output. Yes.
The output. So it's not only difficult to simulate classically that many neurons, which is a very small number, but also they couldn't run it on a real quantum computer. That would require how many qubits here? 8 qubits?
Yeah. Well, 8 plus the output, I guess, whatever, 9, maybe.
So it was even hard to run a neural net that small physically.
Yeah, this is for sure, right? Like I told you, I think
that's crazy. I mean, that means that it's super far from being useful. I mean, obviously you have Moore's law or whatever. Maybe Moore's law is applying to quantum computers now. I don't know. The 72 qubits are highly imperfect. Yeah.
Yeah. In addition to simulating behavior. Yeah. So they're saying with the best supercomputer, they can simulate 50 qubits.
50 perfect qubits.
Yeah, with the best supercomputer, they can get 50. They can simulate 50 perfect qubits.
Okay, and this is not the IBM one.
No, this is a classical computer. This is classical.
Oh, to simulate. Yeah, I'm talking about like a real quantum computer. Like
they have. Well, at the time of writing, they had 72 qubits, right? Imperfect ones.
Yeah. Okay.
Now it's on the order of 100. I think we have access to now.
And it's like it's not on the cloud. It's not like you can just hop on.
No. I think it's like Google or whatever. Whoever has it. You know.
Okay. I see.
And they're running experiments on it. You know, and just trying to.
But I'm sure like this is Moore's law is applying to this as well, right?
It's tricky because now the limit of this will be like the size of an electron, say, or whatever, you know. It's like really a cut. You can't get smaller than an electron, right?
Wait, why smaller? Don't you just want to add more qubits to your system?
Yeah, what I'm saying is like I guess Moore's law is this scaling property, right?
Yeah.
We're reaching fundamental limits is my point.
Oh, in terms of like density.
Or whatever you want to call it. We're really pushing the boundary of how small we can make things, what we're interacting with, you know? Like I don't know exactly. Like a quantum system has to be small.
Yeah.
We're reaching the smallest quantum systems we can actually interact, or close to the quantum things we can.
Wait, why does it have to be small?
Because you want to interact, like big things don't interact quantum mechanics. I mean, they do, but it's very hard to see quantum mechanical things with big objects.
Well, in my mind right now, I have like a grid, and like on that grid, there's like an electron at each position.
Why at each position?
Like, let's say you have 8 qubits.
Yeah.
There's a qubit in position 1, qubit in position 2, qubit in position 3.
Sure, you can think about it like that. Yeah,
and then
it's like what does it mean to? How do you put an electron in position 1?
I have no clue.
Yeah, you have to construct these microscopic or nanoscopic objects, right?
Sure. Objects but you can just scale that up. Like you can just add more. Like you can make your surface larger, right? The size of the electrons is still an electron. It still has the same quantum properties.
Yes, but you have to be able to control which electron interacts with which other electron. Say.
Okay. Sure. Yeah.
It's very difficult to pick which two electrons will interact with each other.
Sure. Yeah.
Without interacting with the other one, say.
Yeah. So the more you introduce, the more like incoherence you have to deal with, right?
Yeah.
So more possible connections.
You do lose coherence as you yes. There's a bunch of problems. You know, you have to be at extremely cold temperatures also, right? That's another problem.
Yeah, like the COVID vaccine. Yeah.
Very similar.
Minus 70 Fahrenheit.
We need the army to do this quantum computing. But yeah, I don't know. I'm sure they could have simulated this somewhere. I think it would have been much cooler if they did, right?
If they simulated it?
Somewhere. They did. Used an actual quantum computer to solve this.
Do you think that would be much cooler? I mean, it's the same result, huh?
No, yeah, I know, but it's like, look, we're at the stage where we can do something useful with a quantum computer, say.
Yeah, but this neural net is very far from useful, right?
Yes, I know. But
okay, I see what you mean. Yeah. No, it's like you said, factoring the number 8. They actually factored the number 8 on a quantum computer.
Yeah, with like electrons moving in space, like or whatever.
Sure. Yeah. The other thing is like a DNA computation also. Maybe we can look at a paper on that.
People do that? I don't know.
Yeah, I think so. Like you can have like sort of biological processes, like because you have like molecules that interact with each other and they bind or don't bind. And like you can sort of add like fluorescent markers to them.
Oh, I
So
see.
that like if they actually do interact, you see fluorescence.
It's like a statistical computer or something.
Yeah, I guess. Yeah, I mean, you don't get any superposition. I don't know what kind of advantages you would get to doing that, but people do that, I mean, you can also like write down, you can encode information on DNA and things like that.
Cool.
But I don't know if it has any good theoretical properties. I mean, yeah, I didn't know about this like fundamental limit. I thought like we just had to wait until, they exponentially increase the number of qubits they can.
No, sorry. My fundamental limit thing is like, I'm just saying that we're approaching, like technology, technology usually we get smaller with things. We get,
Yeah.
That's how things scale, right? The number of chips you can put on the number of transistors you can put on a chip. We're reaching the point where we have single electron transistors,
Yeah.
We're not getting smaller. Well, it's going to be very unlikely to get smaller than that.
Yeah.
So the next step will have to be some paradigm shift, which will be maybe quantum computing. But I don't know how long that's going to take to like. It's like a discontinuous jump somehow.
Oh no, sorry. Yes, I think maybe I didn't explain like this fundamental limit you're talking about with Moore's law is addressing the fact that, like you said, the sort of the transistor size is reaching a fundamental limit, right?
Yeah.
But I'm saying like, do you think that we can apply Moore's law to the number of qubits on a quantum computer? Like, is that going to grow exponentially?
I would assume, I think it'll be discontinuous again, right? We're going to figure out something that lets us couple qubits selectively.
Yeah.
And then we'll do it to larger and larger systems. And then,
okay, cool.
I'm sure the first computer had like had 16 bits or whatever,
Yeah, exactly.
And eventually they just figured out things that made it work. The thing is,
do you see, I mean, like you said, there's this like fundamental physical barrier to like how condensed you can make a chip, a classical chip.
Yeah, but for example, like we're approaching absolute zero, right? We're going to millikelvin temperatures.
Sure.
Like 300 millikelvin, say. Right? I can't go much lower already,
But do you need to go much lower? Like I thought that just needs to be the environmental conditions.
Well, the colder it is, the better it is.
Sure. But also like, oh, I see. So if it's the colder it is, the less like incoherence you have and all that stuff.
Yeah. Because less thermal fluctuations will let me jump out of my state, say.
But maybe you can design qubits that are more stable even at higher temperatures.
Yeah, people are trying that.
Okay.
But you lose other properties. I'm just saying like we're for a lot of things where I think we're approaching some limits that we will have to figure out other ways to overcome them, right?
Okay, I see.
Like I think for classical computers, you could have just said, okay, we're just gonna make it work and then we'll figure out making it smaller. Now it's like the making it work thing is like I can't go more colder, or I can't.
That's interesting. I mean, I was pretty surprised by this paper, honestly. Like, maybe, I mean, I just picked the first sort of quantum machine learning paper I could find, but it almost sounded like this is sort of already being deployed, and it's like, quantum computers are here. That's why I'm wondering maybe if quantum, like the D-wave stuff, is more advanced and it can be applied in similar ways.
We have hundreds, maybe 100, on the order of 100 qubits, right?
Yeah, but I mean, that's
D-wave is a quantum annealer. It's not. It solves very specific problems.
Yeah.
So it's not universal in the sense that you can't just do a computation that you want. You can't put the gates like I showed you.
Yeah.
On that. I can do this with D-wave. I can do a very specific calculation.
For sure.
I don't know if we're there. I don't think we're there, right? We're not there. We're not doing useful things, I think, with quantum computers yet.
Interesting. Okay, well, maybe we'll bring Alessandro back for a quantum annealing episode.
Sure.
All right.
It's already 6:40 our time.
No, it's dinner time.
I think we busted the clock here.
Yeah, it is dinner time. Okay, well, next time we will have, I think, a bio paper.
Oh yes.
I'm very excited. Yeah.
As am I. Okay, well, thanks, Carlos.
Thank you, Perry. I asked a lot of questions, and I think I learned a lot.
That's good. I also learned.
I learned that 8 neural net is barely doable on a quantum computer. I was shocked.
Exactly.
I was pretty shook when I saw that, as it were.
There you go.
All right, well, keep plugging away at the quantum computer. I'm waiting for it.
Yeah, well, I'm not doing that really.
Well, you're making a better qubit, aren't you?
We'll figure it out eventually.
All right. Next time. See you next time.
Yeah, see you later.
Ciao.